Welcome back, everybody. And off to the races. Practice problem 6. 5, the alternate 4 was 5, and it really was the same as 4, so we can skip 5. We're moving on to this one. We have a 6 and a 6 that I doctored just now with just slight changes to illustrate a good point. So our analysis of Rx, do not be confused by the Rx being on the right side this time. OH is not a leaving group, right? So OH is not in Rx ever. That'll be the nucleophile right there, and a reaction where there's no solvent, it will also be the solvent. This is the Rx, it is secondary. So Mabarov. My pen's off. Interesting. Secondary, don't know. Secondary, don't know. Okay, nucleophile, blue new. Neutral oxygen poor favors SN1. Neutral sulfur, nucleophile is neutral sulfur, RSH. Not strong, that'd be S minus strong. This is moderate. We are still in the unknowing stage. That's what you do for moderate. Solvents are never having an unknowing stage. You're in a category, you always have a conclusion for solvent. Better call solvent. In the top one, the solvent's also ROH. Polar protic. H bonded to O is a hydrogen bonding solvent. Those are called polar protic. They also favor SN1. In your conclusion, much the same as before, based on red and blue, is SN1. Solvent down here is diethyl ether. Yes, ET is a short form for ethyl. That's diethyl ether. Here, I'll even draw it real fast. Nonpolar favors SN2. So I got two things saying I don't know, and only one thing making my mind up in this one, the bottom thing. Sometimes you go all the way to solvent to make your conclusion. SN1. So you're ready. You're ready for the product. You say, okay, the nucleophile ends up on the carbon with the leaving group, and the stereocenter gets racemized. But I'm just going to write 50-50 R and S. And I'll draw what you get, and then you'll say, Dr. Whitaker, you just made a mistake. And I'll say, no, I didn't, because I remember something about carbocations from chapter 6. And something about being allylic from chapter 8. The nucleophile is going to end up here. That's where you're thinking I'm making a mistake. CH2C with a V. And there you're going to write 50-50 RS. And then we're going to talk about that for a second. You're not going to let that go, are you? 50-50 RS. So why is it there? Well, you just need to look at the cation. Just need to take a boo at the cation, which ends up one away from being allylic. Okay, not adjacent, but adjacent to adjacent. And there's an H right here. Now I know we only did rearrangement if there was a branched carbon, but this is even more important than branching. If I can move that to there, I'm going to generate a very stable carbocation. Right there. secondary allylic is as stable as a hypothetical carbocation 2 plus 1.5 equals 3.5. I don't think I should have used red. That's more stable than any cation you've seen to this date. Up until now, you have believed that tertiary carbocations are the most stable carbocations possible. You didn't know enough yet. Being allylic, or what's the other word? When it's not a double bond next door, but it's a phenyl next door. That was called benzylic. I'm going to write this down. There you go. Being allylic or benzylic adds 1.5 degrees of stability to the cation. Take that to the bank. It's a guideline. It's not an exact thing, but it's pretty good. And yeah, it gives us numbers that are not nice, but they're, let's see, what am I trying to do here? One thing at a time. Trying to move it. And I'm going to make it fit. Nope. There you go. There's the 1.5, 3.5 degrees. If you can make a cation by rearranging a cation that used to be secondary, then you must do so. If you can get it to be more stable. That is the same as you learned in chapter 6. Why do rearrangements happen? To get a more stable carbocation. The only thing that's new here is, why is this a more stable cation? Because being allylic means you can resonate. Yeah, isn't resonance more important? I'm going to write that down. That's resonance right there. Ugh, didn't go well there. Wow. Resonance. Equal stability. Resonance is more important than hyperconjugation. Yeah. Hyperconjugation is actually pseudo-resonance. That's what that means. Conjugation is resonance, but it's not quite resonance, so they threw a hyper in front. The real resonance is even better. So yeah, why did it happen? Because we made a more stable cation. Secondary allylic is as stable as, looks like secondary allylic as the word is part of it. Is as stable as 3.5 degrees. All right. Now in the reaction down here, solvent doesn't allow put that in red. This solvent does not allow, will not allow a secondary carbocation. Remember, secondary needs a little help. So if you can't have a secondary carbocation, then you can't have a rearrangement from the secondary carbocation. Why? Because there's no secondary carbocation to rearrange. So you got to have what kind of solvent? What's the only solvents that help cations? Right here, polar protic. Polar protic solvents. I can't make this point heavy enough. Secondary C+ will only occur in polar aprotic solvents. So I don't want to see an SN1 conclusion down here. I don't have a polar protic solvent. I said polar protic again. Twice today. When did we have the carbocation? Polar protic solvent. Why did I write polar aprotic? Because my brain is broken. Polar protic solvents are the ones that let cations happen. I hope my mistakes are not throwing you off. Hopefully, by seeing them happen and me being so mad at myself, you will correct it before it happens again. And put that back there. Moving on. SN2 reaction. What's going to happen to your stereo center? Don't write 50-50 RNS. There's a backside attack in an SN2 reaction. Backside attack. So we got this. There's no rearrangement. Nucleophiles coming in behind the wedge. And it's going to be on a dash to a sulfur with an isopropyl. And a hydrogen got pushed out front. Now you're saying, wait, where did the H go off the sulfur? Good question. I'm going to put it here on the molecule and get rid of it very shortly after you figure out why. If an oxonium has a pKa of -2, and there's a trend on the periodic table in acidity as you go down a column that the acids get stronger, then what's the pKa of the sulfonium? All you need to know is it's less than -2. Do we end with strong acids? I hope I was clear earlier in this lecture that we do not ever end a reaction with a strong acid product. We neutralize it with the solvent. And there's the neutral sulfur compound. And if you're curious what this functional group is called, it's a thioether. What's thio mean? Sulfur has taken the place of an atom, usually oxygen, and that's what it took the place of in the name ether. So if it was an O there, it'd be a normal ether. If there's a sulfur, it's a thioether. And I think we can do the next part. I'll have you take a look at the next part. Practice problem 7. I have 2 copies of it here. Just do the second one. You take a look at that. Carbon with a leaving group looks like secondary again, but I think if we can make a cation, it's going to rearrange to our best cation so far. Why am I saying that? If I can make a cation here with a polar protic solvent allowing that, which is what I have here, polar protic solvent will allow a cation right there, then all I have to do is move this H here and I'll have a tertiary cation that's also allylic. How stable is that? What are we supposed to do when you're also allylic? You're going to start with tertiary and add 1.5 degrees and get 4.5 degrees of carbocation stability. We have not seen anything like that so far. SN1 is definitely where we're going here. Carbon with a leaving group starts off secondary. So originally, I don't know if it's SN1 or SN2. This nucleophile has us leaning towards SN2. So you're thinking, I'm going to just go to SN2. Strong is the category. SN2 is the conclusion. But keep in mind, solvent, polar, protic. Just a comment down here. You don't need this in your answer. Allows secondary C+, which can, here's my symbol for rearrangement, to tertiary allylic. How stable is that? 3 plus 1.5. Once again, it's not a quaternary and a half carbocation. its stability is as if it was a quaternary and a half carbocation. Polar product SN1, and SN1's happening. It overrides this because this is the bee's knees of carbocations right here. So you're going to get a cation here, move the H there. So I'll have two H's there. That won't be a stereocenter anymore. When the H moves, it won't be a stereocenter, but this will. And you're going to get the nucleophile. Hey, which one's a better nucleophile? S minus is a much better nucleophile than O. It will react. There's the original. Sulfur with a propyl has been neutralized by the solvent. You need to acknowledge the stereocenter in an SN1. It's 50-50 mix of R and S. Right there. And that will be our stepping point for our next segment. And we're going to talk about elimination. Elimination has two types, E2, much more common than E1 for reasons which we will discuss. And I will see you to do that discussion very soon.